Buffer solutions, introduction and uses. Let's first of all introduce what are buffer solutions. Solutions which resist changes in pH when small quantities of acid or alkali are added. Conversely, a buffer solution, more precisely pH buffer or hydrogen ion buffer, is an aqueous solution consisting of a mixture of a weak acid and its conjugate base, or weak base or its conjugate acid. So the first combination is suitable for the acidic buffer solution that maintain the pH less than 7, whereas the second combination is usually known as alkaline buffer, which manages the pH higher than 7. The pH of the buffer changes very little when a small amount of strong acid or base is added to it. Buffer solutions are used as a means of keeping pH at a nearly constant value in a wide variety of chemical applications. In nature, there are many systems that use buffering for pH regulation. For example, in biological applications, in biological systems such as saliva, stomach, and blood. It is essential that pH stays constant in order for any processes to work properly. Most enzymes work best at particular pH values, so it is important to control the pH of these biological systems. So now let's consider an example of blood, how the pH of the blood is maintained. The pH of blood is normally about 7.4. If the pH varies by 0.5, it can lead to unconsciousness and coma. So let's see how the pH of the blood is maintained. Carbon dioxide that is produced by respiration can increase the acidity of blood by forming hydrogen ions in aqueous solutions. So using the equation, we can write that the carbon dioxide, when dissolved in water, that is dissociated into hydrogen ion and bicarbonate ion is produced. So let's see, if we add acid to blood, it will generate excess of protons. These protons are that are accessed are removed by the bicarbonate ion in a reaction to produce carbonic acid, and this carbonic acid is dissociated into carbon dioxide and water, that is removed using blood circulatory system. Now let's discuss other uses of buffer solutions. So the first one is washing powder that maintains the pH of the detergent solution, so detergent can work in its pH range properly. Eyes also have a specific pH, so the eye drops containing the buffer solution, so that's why any irritation that is causing the pH change in eye, it can be neutralized using the eye drops which contain the buffer solutions. So here we have discussed a few of the common examples of buffer solutions that are used in daily life. So let's discuss how buffer solutions are able to control the pH of the solutions. So this kind of performance is known as action of buffer solutions. Now let's first discuss about acid buffer. It is essential to have a weak acid. That is for equilibrium to be present, so that ions can be removed and produced. This dissociation is small and there are few ions, like we have a weak acid that is dissociated into ionic species. So the concentration of the undissociated form is high as compared to the low concentrations of the dissociated species. For the formation of buffer solution, a strong acid can't be used, as it is fully dissociated and cannot remove hydrogen ions. For example, if we have hydrochloric acid, when dissolved in water, it will completely dissociate it into chloride and hydrogen ion, and the relative concentration of the ionic species is high with negligible undissociated form. Now let's discuss adding acid. Any acid added to the solution generate protons or hydrogen ions that is removed by reacting with acetate ion to form acetic acid via the equilibrium reaction. So for the weak acid, unfortunately, the concentration of the acetate ion is small. Why? Because the acetic acid is not completely dissociated into its ionic species. So we need the high concentration of this species so that when an acid is added to the solution, this species must react with acid, that is the reaction of this species with the proton to make this acetic acid species. So for this purpose we need a system that can generate the excess of these species, but it must not increase the concentration of hydrogen ion. For that purpose we need an external source which can increase the concentration of this acetate ion. Why? Because the concentration of the acetate ions is small and only a few hydrogen ions can be mopped up. A much larger concentration of acetate ions is required when an acid is added to the system containing the acetate ion and hydrogen ion as well as acetic acid. So what we will do to build up the concentration of acetate ion, sodium ethionate is added. So what is the sodium ethionate? Sodium ethionate is the IUPAC name of sodium acetate, that is usually abbreviated as the salt of the acetic acid. When dissolved in water, it is dissociated into acetate ions and sodium ions. So what happens if we add an acid to the solution containing acetic acid, acetate ion and hydrogen ion, and as well as we have added a new component that is known as sodium acetate, which is producing acetate ion in excess. So by adding hydrogen ion to the solution, these acetate ions will neutralize the pH of solution by converting the acetate ions into acetic acid through an equilibrium reaction. It means that for the formation of an acidic buffer we require a weak acid and its strong conjugate base, or we can call it salt of strong base. So this base is actually formed from the reaction of acetic acid and sodium hydroxide to give sodium acetate and water. So here the sodium hydroxide is actually the strong base and the acetic acid is weak acid. So this one is the acid of strong base. Now let's again consider the dissociation reaction, that is the formation of acidic solution through the dissociation of acetic acid. Now let's consider the addition of an alkali. Alkali generate hydroxyl ions when dissolved in water. Although they do not appear in the equation, they react with hydrogen ion to produce water. So the removal of hydrogen ion from the weak acid equilibrium means that, according to Le-Chatelier principle, more acetic acid will dissociate to form ions to replace those of being removed. So here we have an equilibrium that is established between the acetic acid and the dissociated species, and when the alkali or the base is added to this solution, the base will react with hydrogen ion to generate water molecule. It means that the number of hydrogen ions are decreasing. As a result, the acetic acid molecules will dissociate to maintain the specific concentration of hydrogen ion that is defined by the Ka value of this acid. So obviously there must be a large concentration of undissociated molecules must be available. The important point is the concentration of buffer solution is also important. By changing the various ranges of buffer solutions can be prepared using different concentration of weak acid or base and strong conjugate base or acid, depending on the combination we are going to prepare. So another important point is, if the concentration is too low, there won't be enough concentration of acetic acid or acetate ion to cope with the ions added. Now let's summarize the acidic buffer solution. When an alkali is added, it must require high concentration of hydrogen ion so that it can neutralize the hydroxyl ions to water. So for this purpose we need large amount of acetic acid form so that it can be able to provide the hydrogen ion through dissociation. And for the acidic buffer, when an acid is added, we require large concentration of acetate ions. Why? Because these acetate ions from the buffer solution must neutralize the hydrogen ions to make the undissociated form, that is acetic acid. So when an acid is added to the buffer solution, we need excess acetate ion that can be provided by adding salt, that is the strong electrolyte which can be dissociated completely to acetate ion, so that enough or excess acetate ions are available to react with hydrogen ion and produce acetic acid. So in this way the weak acid provide the equilibrium and large undissociated concentration. The sodium salt provides the large dissociated concentration. So in conclusion, when an alkali is added to a buffer solution, we need excess of weak acid that can be dissociated to its ionic species and providing the hydrogen ion, and for the addition of acid we need excess of acetate ions which can be obtained by adding the salt of strong base which give the strong electrolyte salt. So now let's discuss how we can calculate the pH of an acidic buffer solution. For example, if the concentration of the acid and the conjugate base or the salt is given with the value of Ka, using this formula we can calculate the concentration of hydrogen ion, and then using a relation that is pH is in the negative log of hydrogen ion concentration, so it will give the value that is 3.699, so equal to 3.7. Similarly, for the formation of alkaline buffer, we need a weak base that must not be completely dissociated into its ionic species, generating the low concentration of the hydroxyl ion and high concentration of the undissociated form. So making a buffer solution that is alkaline buffer, we need two things. Number one is a large concentration of hydroxyl ion when it is useful to react with any of hydrogen ion added. It means when we add an acid, it will generate hydrogen ion within the solution, and these hydrogen ions must react with hydroxyl ion that must be provided from the solution in large excess. So the concentration of hydroxyl ion is low. So how this can neutralize the hydrogen ions? It will neutralize when the hydrogen ion will react with the hydroxyl ion. It will generate water molecule, and thus the undissociated ammonia will be dissociated into the hydroxyl ion and then again neutralize the hydrogen ions. For this purpose we need excess of ammonia that is undissociated. And for this basic buffer solution, when an alkaline source is added that will generate excess of hydroxyl ion, these excess of hydroxyl ions must be neutralized from the excess of ammonia ion, that is ammonium ion. So for the large concentration of ammonium ion we need a salt of weak base and strong acid. For example, ammonium chloride. So this ammonium chloride can provide the excess of ammonium ions. As this salt is strong electrolyte, it will generate the excess of ammonium ions and chloride ion when dissolved into the water. So it is dissociated completely into the ammonium ion and chloride ion. So this ammonium ion can neutralize the hydroxyl ion by reacting to form ammonia and water. So in this way, for alkaline buffer solution, when we have excess of alkali, it can be neutralized by adding the ammonium chloride salt, which can be dissociated completely into ammonium ions. These ammonium ions can neutralize the added alkali to water and ammonia. So for the addition of alkali, we need large concentration of ammonium ion that can be provided by adding the ammonium chloride salt, or for addition of strong acid to the acidic buffer solution, we need excess of undissociated ammonia. So this ammonia can be dissociated to generate hydroxyl ion. So these hydroxyl ion can react with hydrogen ion of the added acid. So they generate the water, and the new upcoming hydrogen ions can be neutralized by the dissociation of ammonia that is available in excess to provide the excess of hydroxyl ions.